Hi, friends. Welcome again to another episode of Beyond the Clouds, Edge to Edge Transformation. And speaking of transformation, the electronic design industry has been a big part of it. They create the hardware infrastructure that we need to run the cloud, the edge. And I was fortunate to have known Janet Olson from the early days of the electronic design space, particularly at Synopsys and later at Cadence also. Janet, tell us a little bit about your story. How did you end up joining EDA and coming to where you are today?
Okay, thank you, Shankar. Yes, as Shankar mentioned, we've worked together for quite a while in EDA. I've actually always been in the EDA industry. I graduated with a bachelor's in electrical engineering. And what drew me to EDA was really that it was the intersection of software and hardware. So I could see the promises I was interested in both. And what EDA allows you to do is both software for hardware design. So you really see that interesting intersection of how do you build hardware, but do it using software. So my first job out of college was working at Amdahl in the test EDA area. And that was back when most of the EDA was done by designs company specific. I then very quickly moved over to Synopsys. I moved at Synopsys about a year after it went public. So when I joined, there was only about 600 people, and Art was welcoming everybody new into the company in his weekly meeting. So it was very nice to be part of that. And actually, I was at Synopsys from the point that it was at 600 people to when I left, it was over 10,000. So being there and being able to see that growth was very interesting. This is really growth in terms of spreading out to new areas, the people evolving, and also just the technology, seeing how the semiconductor industry grew and its new challenges and how the EDA software was able to work to resolve those challenges. So while at Synopsys, I started off in test as a software engineer. That gave me a good introduction to the different areas. And then from there, I moved over to power. I was actually working in power analysis and optimization long before I think many people were interested in that power optimization. From there, I moved to physical compiler, which is the back end, and was able to get exposure to signal integrity, timing, as well as extraction. So that really gave me a rough, very broad strokes of all the different areas of the design implementation flow. From there, I moved over to design compiler. And from there, that design compiler is the first product of Synopsys and is still continues to this day to be one of its cornerstone products. Also at Synopsys, I was able to grow through the leadership ranks and really appreciate the support that I had there. I found that it was interesting and rewarding to be a software engineer and be able to produce my own code. But what I found is that through a leadership positions, first as just a developer, and then as a manager, a director, and eventually a vice president, is that I could have more influence through working through others. With it, I think the very unique part about EDA is that it is a very technical job. You actually you have a broad exposure both to the entire semiconductor industry because you're responsible for solving the problems of it. And in terms of even software, the problems that you solve are very wide and diverse. You actually, the whole semiconductor industry relies on the EDA software to be able to design the chips. It's too difficult to do that now by hand, or even for someone to be able to do that in-house anymore. So being able to see what are those problems the semiconductor companies have and being able to figure out how do we solve them, through new advances and, what's the latest products that they have to use, what is the latest technology that's available. All of those things I think are very interesting. So while at Synopsys, I was fortunate enough to become the first female VP of engineering. After being at Synopsys for over 20 years, I decided that I wanted to really get some exposure to some other areas, and the next level position came up at Cadence. So in that, I was responsible not just for synthesis, but also for test, high-level synthesis, and formal verification. So I moved over there, and I found it was very interesting that although Cadence and Synopsys have similar sets of products, they come from a very different background. Cadence came from more of a sum of parts. So there's a lot more of a business focus on Cadence. So what I found is, in addition to being able to work with customers, understand semiconductors, and solve challenging technical problems, I also was exposed to the business side as well, which is really part of the whole ecosystem. So that's where I am today, running several different groups in Cadence in the front-end design space.
Janet, I remember the good old days of DFT, which was considered not as important as performance and new technologies. And later came power. Again, it was like a second or a third thought in people's minds. Where do you see it going forward? Because I've heard that there's not enough energy in the world to support complete automation and to have ChatGPT or any kind of automation. We don't have enough energy. What can we do to make it feasible to have these technologies become real?
Yes, as you say, some of these technology, many of these foundational technologies have been around for a long period of time, but what you find is that as time progresses, there's different emphasis on other areas. Back when I started in power, it really was a second or third order concern. But now what we see is that power tends to be people's first concern. And that really is because of, part of the amount is the work that we're doing. It's also the fact that how pervasive semiconductors have become. You actually, right now, semiconductors are everywhere. You have your car is full of thousands of them. You actually have a pacemaker. You have your phone, which becomes an attachment. Even when you're going in a race, you actually have a little chip in the bottom of your shoe to figure out when you cross the line. So between IoT to large scale, the cloud, there's semiconductors and semiconductor use everywhere. So that really requires that the power. Even the new technologies like AI, they obviously require a lot of compute. And so the power concerns are becoming more and more. So what I've seen now is that first, the power is front and center in terms of the objectives when people design their chips. And I think that will even go even more so. The other area you mentioned is DFT, design for testability. Test historically has been an afterthought. It's something where you design your chip, and then later on you say, okay, if it's going to take me a little while to test it, maybe I'll add in some additional hardware to enable me to do that. So that's become that everybody now recognizes that with a complexity of chips, you have to have test and design for testability logic embedded in your design. So it's there. It actually can take up to 5% logic. And what you see now is that you have companies that actually have trouble taping out their design because sometimes if they insert it too late or don't pay attention, they can have a glitch because of the DFT logic. So it's become a mainstream part of the whole ecosystem, of the whole design flow. Another thing is actually, even for the future, there's the next stage, which is silicon lifecycle management. That's the idea of, right now, many companies, Tesla already has the ability to test the system when it's, running, right? When you go to a Tesla car, it sends the information back and they can actually debug and figure out where the problems are. There's actually an opportunity for EDA to actually introduce or have more products directly in that silicon lifecycle management phase. It's really, in terms of test is the basis of that. Test is what creates that test logic where you can actually send patterns to it, you can figure out what's happening. And the fact that now you can have in-system test where you can, no matter where that system is, you can actually over broadband be able to send the patterns there, figure out where the problems is, this can be, not just used for Tesla, but really be used for anything else, even say, for example, even your dryer, which has a lot of semiconductors. If you can actually go and send from the system, be able to remotely diagnose it, especially with, the DFT hardware, software to be able to run it remotely. Also with all of the AI technologies, combining that with timing information, all the aging information, and all the information about crosstalk and design margins, you can actually be able to very accurately diagnose what's happening in field. So these are kind of some areas where we'll continue, that's where DFT was, and I think where DFT will continue to be. I think there'll be more and more of a focus on that area.
Indeed, from the ability to just do basic testing to built-in self-test, and now silicon lifecycle management, we've come a long way. And what about hardware and software? There was a time when hardware and software were completely considered separate disciplines. Today, we know in EDA, you cannot build hardware without good software. That's the EDA industry. And looks like in future, software and hardware have to work in tandem, software-driven hardware. What are your thoughts on that?
So I think we're seeing that everywhere, right? We are seeing that now. I think they saw software-defined hardware is really where the new realm is. But you can see now it's obvious for everything for what's happening for AI. You see that GPUs are much better suited for AI than basic CPUs. And that is because depending on what the software is that you're going to run on top of it, the hardware underneath needs to be customized. And so we are seeing that more and more where, even for Cadence has Tensilica, and then people write accelerators on top of that and decide, basically it depends on which part of the software needs to be faster. And then you can put whatever part of the software needs to be faster and more customized, you then put that in hardware. So this, I think, multiple companies are doing this already. I just, last year I was at the ARM partners meeting. And what was interesting is that, obviously ARM is known for its CPUs. The first discussion was having the hardware, software, and the systems guy together in a forum to talk about how they all work together. One of the interesting things that the software guy said is that you can make all the hardware you want, but if software doesn't use it, it's dead. So you really need to be able to design them together, and you need to be able to understand what are the needs of the what are the software needs to be able to accurately do the hardware. And I think what you'll see is going forward, especially with the needs for more and more intensive compute, is that it is more important to put some of those software pieces in hardware, or even in prototyping, you can actually move some of the hardware pieces to software so that you have the ability to really try different things. But I see now, as you said before, it used to be very separate. There was a software group and a hardware group, and now I think it's a continuum. And I think that will continue in the future as well. One of the other products I have is high-level synthesis. And in high-level synthesis, one of the biggest uses you would use high-level synthesis for is for accelerators. We see a lot of use of that. And I was just recently on a panel in DAC, and we were talking about that with different university professors about some of the applications there.
Yeah, there's acceleration of different parts of the whole value chain now. In terms of your transition I remember you're always a deep technologist, and from that to get into engineering management and later into executive management, what was that journey like? And is that journey something you would recommend more people take on in their careers?
So for me, I think it was something which fit what I, in terms of my skills and what I was interested in. One of the major advantages of EDA is that you are able to, as you move up the leadership chain, to still also stay technical and use your technical skills. That was something which I also found to be very interesting. And it's really because you have to understand what the customer needs are. in order to be able to be successful in your job. For me, what I found is that I enjoyed solving the technical problems. But what I found was more interesting for me was to be able to work through other people and enable other people to be successful. So being able to work through others and also see a greater breadth of different challenges was interesting to me. I also find it's also very interesting when you see the breadth of problems and challenges, then any one little thing, you see the context of it and you see the bigger picture. So that's something that I enjoyed. I think that there's a lot of opportunity for multiple people to take advantage of the leadership opportunities. I think it depends on what is your skill set, what's your interest level. There are some people that just want to sit at a computer and want to work on their algorithm and get one particular program done. But I would say that, especially in EDA, you have the opportunity to make a very big difference. And I think if you can use those skills to be able to enable others and be able to have direct contact and interaction with customers to see what problems you're solving, it is very enlightening and it's also very satisfying. So I would recommend others to do such areas. I think there's a lot of opportunity within EDA for leadership positions. So I think that I would recommend others to do that.
Janet, when you and I joined the industry, EDA was primarily a very masculine space, very few women in technology, and very few people who took leadership roles. And then I saw you, Karen Bartleson, who became the first president of IEEE, Jyotika Tavle, one of the first people to lead Computer Society. What was that transition like, and where do you see the industry today compared to, like, say, 25 plus years ago?
So I would agree with you that this is an industry which has had very few women. I think it has before, and it does continue to have such. When I graduated, I was one of 3 women in a class of 105 for electrical engineering from Carnegie Mellon. Even when I graduated my master's degree from Stanford, I didn't count, but there were also very, very few women. So it is an industry which doesn't tend to have many women. That also becomes a challenge in itself. I think that what happens, I think I've contemplated multiple times, why is that so? And I think one challenge that you can have is that if people don't see models of what somebody that looks like you being able to do something, then it becomes difficult for people to say, oh, I can do that. So I have sat in rooms where I am the only woman multiple times. And honestly, I've become used to it. That is something which, I think is better now. But even especially, and I think now the EDA industry has gotten better at hiring more women at the lower levels. I would say that, as you discussed leadership really comes from starting at a lower level and moving up throughout the EDA industry. We don't tend to bring in leaders from other fields. You usually grow up through the EDA area, and that's really because of the specialty of knowledge. I think in terms of hiring, we may be at 40% women in terms of hiring, but in terms of executive leadership, especially in technical areas, I think it's still in the 10 percentile range. This is really because of history. I think it's also because of how do you see yourself. There's also some people that have different life decisions, right? Sometimes they may have different modeling in their life of what they want to have for their priorities. So it depends on what their personal preferences are. I think with it, you do have to enable a atmosphere or environment where where women can be successful. I think in my career, I have faced a few times of unconscious bias. And that's really what happens is that, people don't see women in this role, so they expect there not to be a woman. I remember there was one person when I was initially going through the vice president role at Synopsys who said, you're not vice president material because I don't look like some of the other vice presidents that they know of. So that is something where I think I would say there's very few people that have conscious bias, but I think unconscious bias is something that is important to recognize and understand. In order to be successful, I think what you need to do is just to be yourself, to work on what is it that you want to do and try to be successful. Another thing that is important to do is, I think, in order to improve the ratio of women in our field are a couple of different areas. There is now more of an emphasis on hiring women. That is important because then, you can focus and understand where they're qualified women. There has been a little bit of backlash on that because there's been some people then say, are you just hiring them because they're a woman? I think that it is very important, or it is a disservice to other women, is that to make sure we hire qualified women. There's a lot of qualified women out there, but I think we need to make sure that everybody understands you're not just hiring a woman for a woman, you're hiring them because they're qualified. I think the most important part, though, to make them successful is mentoring and having them have some sort of support system. If you're one that looks different in the room, no matter whether it's for gender, race, belief system, you want to have somebody else you can identify with. And even through any career struggle, through career progression, you will have different things, which some things go well, some things don't go well. And having that support system or someone who you can talk to be able to give you advice is important. So what I think of one of the most important ways to have women be successful in the field is to have a good mentoring system. That's something which honestly Cadence is doing a better job at right now. I've been mentoring several people, and it really does make a big difference to be able to have someone feel that there's someone they can talk to, someone they can look up to, somebody they can get advice for. And I think that's also your way of paying forward. So I think that mentorship is one of the key areas for this. There's other areas which are also quite useful or quite helpful. One of the other things Cadence does is a Cadence Women's Conference. So this will be the second annual version of that, but just to be able to see many of the women at Cadence come together, have some discussions about topics relevant for them, but basically be able to center and say, okay, there are some common struggles, talk about success stories, but be able to have that support for them, I think, is another area. I would say still, EDA tends to be one of the more technical areas, so there are many fewer women. So I think we still have a room to go, but I can see it improving.
Janet, that's really amazing. Cadence was the first company I joined in EDA, and it's great to see it has taken leadership in many different aspects of the industry. In the United States, one of the impediments to growth is not enough engineers, and we see that globally. How can we help people understand the value of STEM education? And is that something that we as executives or engineers can consciously do to help others go forward in these areas?
Yes, I would say that STEM education in the US is critical, and I think it is at a point where it's quite concerning, the lack of STEM education that we have in the United States. As you can see, I think you talked about it before, Shankar, with the CHIPS Act, they're going to be building all of these new fab plants, and we really don't have the pipeline of engineers in the US to be able to staff them. This is something where if I look into even our educational system, even for my class, when I did engineering, I would say less than half from my bachelor's degree actually stayed in engineering. Even for the ones that actually ended up graduating, a lot fewer actually ended up staying there. I think it is important in general to promote this, raise the awareness of STEM education throughout the entire education system, not just start in high school and college, but in order to accentuate the importance of it, you actually need to start it much earlier. One of the things which was kind of interesting is that there are actually different areas, different groups which are starting some different initiatives. The Women in Semiconductor Engineering, the GSA actually has a women leadership committee, leadership initiatives. They had a talk, and there was a very interesting woman. She was actually the head of Girl Scouts. And what she did was to have a STEM badge in Girl Scouts. And what they did was really to introduce at a very early age. They actually had a ball of yarn, and they had all the girls pass it around. And what they explained to them is that's networking. And I think part of the issue which you have with STEM education for the US is it seems scary. It seems something that's hard. It seems something that's intangible. But just to be able to, have that foresight, I thought the woman was quite interesting to be able to, as a head of Girl Scouts, to introduce the STEM badge by introducing it grade age 8. This is what networking is. You have to gain that interest early and continue it on. And I think that's incredibly important. And without that, right now we do have to import the vast majority of our engineers because they're not being taught through US schools. Even right now, I'm working with a nonprofit called Equal Opportunity Schools, which is trying to get underprivileged and people of color to take advanced placement classes so that they go on to college. There actually have several initiatives there to focus additionally on STEM. But I think there does need to be much more work in order to be able to interest and get people at a very early age to understand the excitement of the possibilities of STEM. For, as you can see, semiconductors and STEM is everywhere. So we want to, I think many people think, oh, that's hard. I think many people can do it. It just depends on, I think we need to get their interest level up.
Indeed. I was telling my plumber who was wondering what education his son should have. I said, I do high-tech plumbing. We build the hardware. Literally, we clean up stuff. We do test and verification and cleansing in some ways. And he was like, his son got very curious, and there's so much to do there. Janet, I know you made many seminal contributions in the industry, in electronic design, every aspect of it. In what ways has your profession changed you as a human being? What were the gifts that you received as a person through this whole work that you've done for the industry?
So I would say in terms of, my personal satisfaction is I do enjoy EDA because I can see what I've done. I can see the direct impact. I think that's something very unique about the EDA industry is that you can work directly with semiconductor companies and partners and really be able to see the effect of what you've done and being able to see it propagate, right? We are at the forefront of all the technology, right? AI, cloud, communications, compute. We can see that. It's interesting, and you can see the direct impact you've had on that. What I've also found is, learned a lot about myself with it. There's been obviously highs and lows. I have been able to fortunately have several accreditations for which I'm proud that it really shows or can allow me to see the contributions that I've had, which are meaningful. Like the DAC award, the Marie Pistelli won, along with my patents, as well as some of the other awards, are meaningful. And getting the various awards enabled me to see some of that impact that I feel is also seen by others. And I think that is very rewarding.
Yeah. Janet, we all have participated in this major revolution in automation and technology. And there's always that fear that comes up. Now it's with generative AI that many jobs will be lost. We saw that from the very early days of the calculators to the computers. But what do you see going forward? Are we actually making humans redundant? Will there be meaningful jobs for people going forward?
I know that people are concerned about that with generative AI. Well, then there would be no longer need for programmers. I think you've seen this through every big revolution. I would agree with generative AI is a major transformation, as all of AI. But what you've seen is that there's a lot of work that humans can still need to do, right? I think as you, just in terms of the Industrial Revolution, with the Industrial Revolution, people say, oh, if you don't do this by hand, what's going to happen to all the jobs? There are other higher value things which we can do and contribute. I don't think, honestly, we know exactly right now the limits of what generative AI can do, but there will be limits. And I think it's really, it's a tool for us to use to really move to that next level. You can see there's overall, we had a talk recently by a Wall Street person who talked about the labor shortage. And really what generative AI, or all AI does, is to address some of this labor shortage. But I think he had a presentation to talk about how there's a labor shortage throughout the entire world. You know, you look at even now, the labor statistics in the US, our unemployment rate is very low. And this generative AI, will address some of the, redundant tasks, which obviously could be automated. But I think there will always be that potential for more. And so what people can make a meaningful contribution for. So I'm not afraid about that one. I think there's a tremendous future and potential ahead of us.
Well, Janet, it's always refreshing to talk to you. I've always enjoyed seeing not only your contributions, but how you've affected people around you. So please keep up the good work. And to everybody out there, I'm always looking for different viewpoints, different ways of doing things, how it's all affecting us with all this new technology. So please come forward. Thanks again, Janet.
Thank you so much, Shankar.